Lumped mechanical systems allow us to model the dynamic response of a system using springs, dampers, and masses. With this approach, we can analyze the force and displacement responses under different excitation conditions. Hello, I'm Armin. In this video, I'll show you how to model the frequency and time responses of a single degree of freedom vibration system subjected to harmonic and base excitations. Before we begin, let's review the basics of the model. An SDOF system is the simplest mechanical vibration model. It consists of three main components: a mass, a spring, and a damper. The entire system has only one independent displacement, represented by x of t. This means the motion of the system can be completely described by a single displacement variable that changes with time. Although this model is simple, it is the foundation of vibration analysis and is widely used to understand the dynamic behavior of many engineering systems. In this example, a sinusoidal force is applied directly to the mass. The expression for the excitation force is shown on the slide. The motion of the system is governed by the equation of motion shown here. The system response consists of two parts: the transient response and the steady-state response. The transient response depends on the initial conditions and gradually disappears because of damping. Once the transient response has decayed, only the steady-state response remains. This equation represents both the transient and steady-state responses. However, as the number of degrees of freedom increases, the equation becomes much more complicated. Therefore, numerical methods are usually the preferred approach. In the next example, the excitation is applied as a sinusoidal base displacement instead of a force. All other parameters are the same as in the previous harmonic response example. The steady-state response is shown here. First, a harmonic excitation is modeled in COMSOL using the following parameters. The COMSOL results are compared with a MATLAB script, and the results are identical. Next, a base excitation is modeled, and the results are again identical using the following parameters. Finally, I'd like to introduce the reference book, Engineering Vibration, by Daniel J. Inman, from which I used the analytical equations presented in this talk. Explanation is enough? Let's get started. I'm going to start by clicking Model Wizard. Since this is a lumped mechanical system, there is no geometry to define, so I'll select the 0D space dimension. Several physics interfaces do not require a geometric dimension. In this case, I want to use structural mechanics. I'll expand the branch, select Lumped Mechanical System, and click Add. In the Review Physics Interfaces section, you can see the dependent variables, including displacement, force, velocity, and others. Next, click Study to choose the study type. I want to perform a time-dependent study because I'm interested in the system's time response. So I'll select Time-Dependent and click Done. In the Model Builder, you'll notice that there is no geometry node. That's because we're using a lumped mechanical system, which is a 0D component. To begin building the model, you can either right-click Lumped Mechanical System and add components such as a mass, force, or damper from the context menu, or go to the Physics tab, expand Global, and you'll find the available lumped mechanical system elements and terminals. A terminal is applied to a single node. Since lumped mechanical elements connect two nodes, every lumped mechanical system requires two terminals so that the elements can be connected between them. Let's start by adding a spring element from the Global menu. In the Settings window, you'll see two nodes, P1 and P2. P1 is connected to the ground, and P2 is connected to the mass. Under Node Names, set P1 to 0 and P2 to 1, where Node 1 represents the mass. Under Component Parameters, enter 800 newtons per meter for the spring constant. In the results section, you can see that COMSOL will calculate quantities such as the spring force and displacement after the model is solved. Next, let's add a damper. Right-click Lumped Mechanical System and select Damper. Just like the spring, set P1 to 0 for the grounded node and P2 to 1 for the node connected to the mass. With these settings, the spring and damper are connected in parallel. Finally, enter 5 Newton-seconds per meter for the damping coefficient. Next, let's define the mass. The mass is connected between node 1 and node 2. Right-click Lumped Mechanical System and select Mass. In the Node Connection section, set P1 to 1, which is the node connected to the spring and damper. Then set P2 to 2, which is the node on the other side of the mass. For the mass, enter 2 kilograms. The next step is to apply a force to node 2, which is connected to P2 of the mass. Right-click Lumped Mechanical System, expand Terminal, and select Force Node. As you can see, a force node terminal is connected to only one node. Set P1 to 2 because the force is applied to node 2. Under Terminal Parameters, specify the force expression. By default, the force is constant, as shown in the equation preview. Since I want a harmonic excitation, I'll replace the constant force with a cosine function. I'll click in the force field, type cos, and enter an angular frequency of 40 radians per second multiplied by time. At this point, COMSOL reports a unit error because the argument of the cosine function must be dimensionless. To fix this, I'll divide the time by 1 second, so the expression becomes dimensionless. Now the unit error is gone, and the force has the correct unit of newtons. Everything looks good. Now we can move on to the time-dependent study and specify the time interval. In the output section, we need to specify the time points at which the solution will be computed. You can enter the values directly or click Range. Set the step to 0.01 seconds and the stop time to 2 seconds. Then click Replace. Now click Compute and wait for the solution to finish. The solution is complete, and it took about 6 seconds to solve. By default, COMSOL plots the force and displacement results. The COMSOL time response matches the MATLAB simulation results. The spring and damper experience the same displacement because they are connected in parallel. You can also click Force to view the forces in the spring, the damper, and the inertial force acting on the mass. Now, let's see the frequency response. To do that, we need a frequency domain study. Go to the Study tab, click Add Study, select Frequency Domain, and then click Add Study. Now there are 2 studies in the Model Builder. Study 1 is the time-dependent study, and Study 2 is the frequency domain study. In the frequency domain study, we need to specify the frequency range. Click Range, set the start frequency to 1 Hz, the step to 1 Hz, and the stop frequency to 30 Hz. Then click Add. Now click Compute. An error appears because the force expression still contains the time-dependent cosine function. A frequency domain study assumes harmonic excitation automatically, so the load should only contain its amplitude. Expand the component node, open the force node settings, remove the cosine function, and keep only the force amplitude. Now go back to the study node and click Compute again. The solution is complete. COMSOL has added the force amplitude, force phase, displacement amplitude, and displacement phase to the results. As you can see, there is a clear peak in the response, indicating the system's resonance frequency. The peak occurs at approximately 3 Hz, which is very close to the analytical solution. You can also view the phase plot to see how the displacement phase changes with frequency. In the next step, I want to model base excitation by modifying the current system. First, we need to disable the fixed support at node 0, which represents the ground. In a base excitation problem, the ground is no longer fixed because it moves with the prescribed displacement. Right-click the fixed node and select Disable. Next, we need to add a displacement node. Go to the Physics tab, expand Global, and select Displacement Node. Change the node name to 0, since node 0 represents the ground. For the prescribed displacement, I'll enter 10 millimeters. However, the base displacement should vary sinusoidally, so I'll replace the constant value with a sine function. For example, I'll enter a displacement in the form of 10 times sine of 5 times t. COMSOL reports a unit error because the argument of the sine function must be dimensionless. To fix this, I'll add 1 over s to the angular frequency inside the sine function. Now the units are correct. Since the external force is no longer applied to the mass, we can delete the force node. The top of the mass is free to move, so we need to add a free node. Go to the Physics tab, expand Global, select Free Node, and set the node name to 2. Now the mass is free to move, while the base of the spring mass damper system follows the prescribed sinusoidal displacement. To make the model easier to read, we can rename the terminals. I'll rename the displacement terminal to Base Displacement Node 1, and the free node to Top Free Node 1. Everything looks good. Now let's solve the time-dependent study. Go to Study 1 and click Compute. An error appears because the time step is too large for this simulation. Open Step 1, Time Dependent. Reduce the output time step to 0.001 seconds and click Compute again. This is the simplest way to reduce the time step, which often helps the solver converge. The solution is now complete. We can view the force response as well as the displacement response. The dynamic response depends on the relationship between the base excitation frequency and the natural frequency of the system. Now let's solve the same problem in the frequency domain. If I click Compute, COMSOL reports an error, just as before. The reason is that the prescribed displacement still contains an explicit sine function. In a frequency domain study, harmonic excitation is assumed automatically, so we only need to specify the displacement amplitude. Remove the sine function and keep only the displacement amplitude. Now I'll return to Study 2 and click Compute. The solution is complete. This is the frequency response of the system under base excitation. That concludes this tutorial. If you found it helpful, please give it a like and subscribe to my channel for more videos.